space fans, and welcome to another edition of Space Fan News. In this episode, Russia successfully launches Spektra-RG, a dual space telescope designed to map the sky in X-rays. This mission, in collaboration with Germany's eRosita system, marks Russia's re-entry into space astronomy and promises to put them in the forefront of X-ray astronomy for quite some time. Okay, here we go. On July 13th, Spektr-RG was launched from a powerful Proton rocket from the Baikonur Cosmodrome in Kazakhstan at 12:31 GMT and heralded Russia's first major space telescope since the Soviet era. Now, I did a very quick search of the history of space telescopes, and I found that the Soviet Union had launched a couple of gamma-ray observatories in 1965. They worked with the French to launch Gamma, which was another gamma-ray observatory, which launched in 1990 and lasted until 1992. And then Russia re-entered the space astronomy business in 2011 with the launch of Spektr-R, which was a 10-meter radio telescope that looked at the structure and dynamics of radio sources both inside and outside of our galaxy. That observatory stopped responding to commands earlier this year in January 2019. Now, Russia's re-entry into space astronomy is very strong and promises to be amazing with the launch of Spektr-RG, which is an X-ray observatory. If everything goes well, once it reaches the operating orbit at L2, then this mission will provide us an all-sky map of the universe in X-rays at energies up to 30 kiloelectron volts. Now, I'll explain more about that in a minute. This map will hopefully shed some light on the nature of dark matter and dark energy. The Spektr-RG observatory consists of two instruments. The first one is the Astronomical Rontgen Telescope, or ART, an X-ray concentrator that consists of 7 identical mirror modules that are coupled with 7 cadmium telluride strip focal plane detectors. That's how they detect the X-ray photons. Now, the mirror modules themselves were developed at NASA's Marshall Space Flight Center. Each module has about 65 square centimeters of effective area and an on-axis angular resolution of about 30 arc seconds. Now, the second instrument on board is called eRosita and was developed at Max Planck Institute for Extraterrestrial Physics in Garching, Germany, and this will be the primary instrument of the mission and has 7 identical Walter 1 mirror modules, same as the other is ART. However, each module contains 54 nested mirror shells in order to meet the required sensitivity. Now, as you can imagine, observing X-rays through a telescope is not a trivial thing. In addition to needing to be up in space where we can see them, anyone who has ever had an X-ray in a doctor's office knows that they are hard to reflect. X-rays tend to go through things, not bounce off them. So designing a telescope to focus them is actually a tough technical challenge. So far, the best way that's been found to focus X-rays is to move them just a little bit when the angle of reflections are really shallow. By making a tube with special material, an incoming X-ray can be reflected a tiny amount at shallow angles. This is called a grazing incident reflector, and basically they just concentrate the X-rays more than they actually focus them. Now, both the Russian ART and Germany's eRosita are grazing incidence X-ray telescopes. The ART instrument, like I said, has 7 telescopes all lined up with each other, and each one of them contains 28 concentric nested shells. Each one are made with a nickel-cobalt alloy. And at the focus of each telescope are special semiconductor detectors. They are known as double-sided silicon strip detectors, or DSSDs, and they're made of cadmium telluride. And that's what records the X-ray photons when they hit. Now, as I said before, NASA's Marshall Space Flight Center made the 7 mirror modules, and Russia constructed the detectors, the onboard computer, and the data memory system, as well as an avionics unit for temperature control and a star tracker for the telescope's guidance. eRosita also has 7 mirror modules, but each one has 54 concentric shells to reflect the X-rays. The detectors used on these modules are based on a design that came out of ESA's XMM Newton mission. Okay, so back to electron volts. Why do X-ray telescopes use these units? Because X-rays are high-energy photons, they have a very short wavelengths, and they're on order of about a few nanometers or so, and that's, just so you know, that's 10 to the minus 9 meters. which is a billionth of a meter. And for reasons I'm not entirely sure of, X-ray and other high-energy scientists tend to use the electron volt as their unit. The electron volt is a unit of energy, and it's the amount of work it takes to accelerate an electron through 1 volt. Luckily, there's a handy-dandy relationship between energy and wavelengths of electromagnetic photons, and so you can figure out for a given energy in electron volts what the wavelength or frequency is we're looking at. And it turns out that hard X-rays, the stuff that the SRG mission is looking at, are in the 5 to 10,000 electron volt range. Longer wavelength soft X-rays are below 5,000 electron volts. Now, because I wanted to know, and I thought you might too, I looked up what energies X-ray machines in the doctor's office use, and I found that a typical package scanner uses between 140 and 160,000 electron volts, which is about 5 times more powerful than what ART will see, and about 14 times more powerful than what eRosita will look at. Okay, so that's what the instruments are on board the SRG Observatory, and after its launch on Saturday, it's now on its way to everyone's favorite observatory spot in space, the Earth-Sun L2 point. And it'll take about 3 months to get there. So in the meantime, mission planners will be checking out the instruments, and they'll start the calibrations and everything that has to be done to get set up. The total mission lifetime is planned to be 7.5 years. The first 4 years will be spent performing 8 all-sky surveys. 8! That's 8 times we're going to see the whole sky in X-rays. And the 3 years after that are scheduled for observations of selected galaxy clusters and other objects of interest. And what do they expect to see? Well, as the observatory scans the sky, they are going to map about 100,000 galaxy clusters out to a redshift of about z=1, and they will look also at hot gas in between the clusters to form a complete all-sky map in X-rays. In fact, the astronomers on the mission say that they will actually see all of the clusters of galaxies above a certain mass that are contained in the universe. All of them. So that's pretty cool. And all these clusters and their masses, and looking at how they evolve over time, will give a good indicator of where all the dark matter is in the universe and how it clumps together. And this map will not only give us the large-scale structure of the universe as it exists today, right now, but it will also show how the cosmos evolved over time. And that will give the ability to see how the universe changed, which, of course, goes hand in hand with showing how the influence of dark energy has over the structure of everything. The X-ray survey is also expected to unveil up to 3 million hidden black holes that are obscured in distant galaxies, and it will also show what's inside our own galaxy and study in detail the physics of galactic X-ray source populations like pre-main sequence stars, supernovae remnants, and X-ray binaries. So with the launch of Spektr-RG, Russia and Germany moved to the forefront of X-ray astronomy with the most important astrophysics venture in post-Soviet Russia. The discoveries heralded by this mission promise to be nothing short of amazing. And as they come in, I'll be sure to keep you posted. But before I leave you guys, let me just talk a little bit about the current flagship X-ray observatory in space, Chandra. The Chandra X-ray telescope was launched on July 23rd, 1999, which means that's just a couple days away, and we're coming up on 20 years of operation with this venerable telescope. Chandra is a 1.2 meter telescope that has about a half arc-second resolution up to about 10 kiloelectron volts. It has 4 telescope modules compared with eRosita's and ART's 7, and it has 58 nested grazing incident shells. The big difference here, though, is that Chandra is not a survey telescope. It's a point and shoot, meaning it looks at areas of the sky one at a time and then moves to another area. SRG will scan the whole sky in X-rays 8 times and will see more X-ray objects than have ever been seen in the entire 50-year history of X-ray astronomy. And one more thing I want to bring up about Chandra's 20 years in space before I go. While Chandra is not at the L2 point like many of the other space telescopes being built today, I mean it's flying about 200 times higher than Hubble, and which is almost 1/3 of the way to the moon, the elliptical orbit is in means that the shuttle couldn't repair it either. It's too high up. So why do I bring this up? because many of you are getting really nervous and getting your panties all bunched up, and I admit I am a little bit this way too, about not being able to repair the James Webb Space Telescope when it launches. Well, whenever it launches, which is currently March 2021, but we'll see. But my point is, just remember, between the Chandra X-ray Observatory, which has never been repaired and been up there for 20 years, and the Soho Solar Observatory, which is at the L1 point and has been up there for 24 years, since 1995, we've got a lot of experience with long-running space telescope missions. I just wanted to put that out there because people forget. We can do this. We can do this. We don't need to be always up there repairing. And I know Hubble didn't set a very good example, but still, we've got two other precedents here. So before I forget, guys, happy 20 years, Chandra. You're doing great for a mission designed to last only 5 years. Well, that is it for this episode, space fans. Thank you, Deep Astronomy Patreon patrons, for keeping SFN going, and to OPT Telescopes, a world leader in telescopes and accessories for both amateur and professional astronomers. And thanks to all of you for watching. And as always, keep looking up.